Hi everyone, I'm Nianyi from Carnegie Mellon University. Thanks for your interest in my work. In this talk, I will tell you about the dynamics modeling of massive black holes and merger predictions in the new large volume cosmological simulation Asterix. First, let me provide some motivation to our work. So the main problem we're addressing with our dynamical model is that in large volume cosmological simulations, the gravity on small scales is suppressed due to the limited spatial resolution. And this prevents the black holes from losing energy efficiently. Previously, there has been a standard fix to this problem. People usually reposition the black holes to the halo center or a local minimum potential point at each time step. However, this method also has its own problem. For example, as was shown in this video on the left, the reposition model does not produce realistic motions, and it can merge the two black holes within about 10 mega years after the galaxy merger. So our main goal for this work is to model and test the subgrid dynamical friction model to efficiently sync the black holes while producing realistic motions. We will then apply this model to the black hole dynamics in the Asterix simulation. Then, using the updated dynamical model, we will calculate the merger predictions and the orbital parameters for the black hole binaries within the Asterix simulation at high redshift. So now let me begin with our model and the tests. So in our model, we correct for the black hole dynamics by adding a frictional force called the dynamical friction to the black holes. So dynamical friction is the deceleration of the black hole due to the overdensity it leaves behind when passing through the stars and dark matter. This force helps the black hole to lose energy and sink towards the center of its host and stay there. In our model, we use the Chandrasekhar formalism for dynamical friction given by this equation. Here I will not go into the model details. Please refer to my paper for more details of our model. But now, because we actually do have a well-defined orbit, we can check the energy of the black hole pairs when we merge them, in addition to the original distance check used by many previous simulations. So this energy check allows us to extend the decay of the orbit before the black hole merged within the simulation. So to test our model, we first use some 15 megaparsec boxes to study the behavior of different models. So in this figure, we show a single black hole's evolution with and without dynamical friction. Here in the top panel, we show the black hole's distance to its host halo center. Comparing with the orange curve without dynamical friction, we can see that the DF model sinks the black hole much deeper to the center of its host halo. We can also see from the second panel that the DF model goes through more mergers than the no DF case throughout the evolution of the black hole. So after looking at this single case, we'll move on to the entire black hole population within the simulation. So here we compare the dynamical friction model with the no correction model and the reposition model in terms of how many black holes are without, how many halos are without the black hole and how many halos are without a central black hole. So first, we note that the reposition model results in a higher fraction of halos and subhalos without a black hole in it. This is because large halos can actually steal the black holes from its subhalo during the flyby encounters due to the over-efficient merging in the reposition model. And furthermore, in the no correction model, we see that most halos do not host a black hole. Most halos do host a black hole, but over half of these halos does not have a central black hole. This is because without dynamical friction, the black holes doesn't sink well. And finally, we can see that our dynamical friction model behaves well in that it leads to the least empty halos and the most central black holes. After testing the dynamical friction model, we apply this model to a 50 megaparsec validation run for Asterix. This validation run covers a wider black hole population compared to the small boxes. And we have a similar seeding and black hole mass function as illustrious as when shown in this plot. So with this similar mass function, we actually predict a few times less black hole mergers within the simulation at all redshift. And this is because our dynamical friction model greatly suppress the merger by extending the orbital decay time. So now we have carefully tested our model, we'll move on to talk about the black hole binaries in the Asterix simulation. So here we showed an example image of the amazing Asterix simulation. And for this talk, specifically, we will show the merger reposition after we account for the binary hardening processes on small scales. We will demonstrate sample cases of black hole orbits within the host galaxies. And finally, we'll show our preliminary measurement of the orbital eccentricities, which is believed to accelerate the binary hardening time. For more results from Asterix, please also see the talk by Nianyi and Colleen DeGraff. So in the merger rate we have shown previously for the validation run, we did not account for any effect of sub-resolution physical processes that assist the binary hardening. We only account the raw mergers in the simulation. But for the Asterix mergers, we now also account for the various small-scale hardening processes as delays to the numerical mergers. Here we adopt two analytical models by previous works. Here we call them SK15 and DA17, and the main paper for these models are listed here. Here we'll not address the difference in great details, but we know that the sub-resolution dynamical friction and the loss cone scattering model in the DA17 paper is more efficient compared to the Chandrasekhar plus the SK15 model here. So therefore, we will actually expect more mergers using the delay model by DA17 compared to the SK15 model. So here we compare the number of mergers after applying the two delay models with our raw merger rate in the simulation. The left panel shows the number of mergers as a function of binary mass. So here we do see more suppression in the mergers from the SK15 delay model as we have expected. Moreover, as we note that in both models, the delay mostly only affect the low mass end of the mergers. In the SK15 model, the low mass merger decreases by almost 2 orders of magnitude compared to the raw merger. And here in the right panel, we show the different merger rate per year as a function of redshift. Here, when we look at all the binary population, we can see that the delay by the SK15 model predicts significantly less merger compared to the raw merger and the DA17 model. However, as we increase the math threshold and only look at the more massive binaries, the effect of the delay model becomes less important. And now, if we only count the binaries with total mass larger than 2 times 10 to the 6, we actually see that they yield pretty similar predictions. So far in our calculation of the merger rate, we have assumed that the binary orbits are circular, but in reality, they're most likely not. So with our dynamical friction model, we have the richer information about the orbit that allows us to account for the eccentricities. For example, here we show some sample binary orbits within the host galaxy. And we can see that there's a large variation in the shape and decay time of these orbits. Sometimes the orbit will gradually circularize before the black hole merge, and other times the orbit retains relatively large eccentricity. So as a first step towards incorporating eccentricity evolution into the binary hardening timescale calculation, we would like to measure the eccentricity of the binary orbits within our simulation before the merger. So now we show some preliminary results for our eccentricity measurements. As was shown on the left, we measure the orbital eccentricity from the shape of the last 3 orbits in the simulation. We take these maximum distance to be the semi-major axis and the minimum distance to the center to be our semi-minor axis in order to calculate the eccentricity. So after making the measurement for all the merging events in the simulation, we end up with the distribution shown on the right. So here, we know that eccentricity is peaked towards the 2 ends, meaning that we found mostly very eccentric or very circular orbit in the simulation. And finally, we also applied different mass cut to the distribution. And we find that this distribution is actually not very sensitive to the binary masses. Finally, I would like to end by saying that this is still work in progress, and our future plan is to calculate the merger prediction with eccentricities taken into account. As we know that the eccentric orbit has smaller hardening timescales. And we'll also evolve the measured eccentricity down to the binary coalescence and see how that affects the gravitational wave observation in the LISA band. So that's all I want to talk about today, and thanks for listening.